Okay, so I consider myself, in some sense, a visual scientist. As in, I look at the natural world to try to understand the processes and what happens with those. And so I make a lot of observations to try to understand early life on Earth, microbial communities, and just sort of explore some of the ideas about where we came from. And as a scientist, we're usually focused on what we're studying as opposed to our process. But our process as scientists is also very important, and one of the great ways that I find working with artists. So I'm gonna take you to three worlds. A physical world, which is shown here. It looks like Dr. Seuss, but this is a real place. A virtual world, where we take our data and manipulate it ourselves, and then a conceptual world, which is the collaborations that make all of this possible. And so I have had the great pleasure to be able to work in Antarctica. And because the continent is isolated, and we've had ice ages, and the interior of the planet, basically everything that's larger than an 1/8 of an inch is extinct. And so you basically have microbial communities. So you have some little teeny microscopic animals, but it's mostly bacteria. If you go back 500 million years on Earth, you only had microscopic organisms. You have to go back a little further than that. But basically, you can go to Antarctica, and it's like traveling back to early Earth, or like going to another planet. We don't know of another one with life, and we're studying the life here. But this is an underwater image. So we're studying photosynthetic bacteria that live in ice-covered lakes. And they get light, a small amount of light through the ice, and they grow in these amazing shapes. And so Dale Anderson is one of the people I worked with, and he's a really amazing underwater photographer. And these little peaks and pinnacles are about that high. His images are pieces of art. One of the things we're really interested in is what causes the bacteria to create these amazing sculptures. We see some similar ones fossilized in the rock record that go back billions of years. If we can understand what's sculpted in these bacterial communities, maybe we can learn something about what was happening for early life on Earth. So one of my graduate students has worked with drop cameras. So this is a GoPro camera that we now know how to turn. We drill a hole in the ice, and these are those same pinnacles. We have a little bolt to show which way's down, because we can't control that yet. But you have this amazing complexity of shape. And it's all from the growth of microscopic threads of bacteria that are photosynthesizing, absorbing nutrients from the water, releasing waste into the water. There's a few hot springs on Earth that have some things like this in sort of small pools, like in Yellowstone. It's a beautiful place to look at them. But this particular lake, one of the things we did in December down there is we drilled a lot of holes in the ice. The ice is 4 meters thick, so a one-story building. And everywhere on the lake floor that was shallower than 50 meters has these pinnacles. And basically there are 1 billion pinnacles or so in this lake, where you take the area. So this is something that early Earth looked like before we got here. So we have this great collaboration trying to understand these beautiful landscapes. But one of the problems is getting to actually look at them. We can drill holes in the ice and put cameras down, but we also send divers down in dry suits. This particular lake has quite warm water. It's slightly above freezing as opposed to exactly at freezing. It takes a lot of, we camp out in this sort of foreign planet. The diver goes down in through the hole in the ice, and we have a rope so that they can find their way back, because they can't bring any data back if they don't make it back themselves. And then we take photographs, make measurements, and collect samples. So I didn't start this work until I was old enough that I didn't actually want to spend the time to become skilled as a diver. So it takes a huge amount of training and a very large number of dives in deep, cold water before you're even allowed to do this. And so I work with my student Tyler here and a colleague Ian Haas from New Zealand and then Dale Anderson for the diving. So I don't get to see these worlds except with the types of things that I'm showing you and the samples, and then some of these beautiful images. And this is where one of the ways that the photography in particular becomes extremely important. So these little pinnacles are about an inch or so tall. And this is underwater macro photography in 0-degree water, or freezing water. You can see the little puffballs at the top. When we take samples, we can actually take those bacteria and genetically classify them and understand what organisms are there. And there's a correlation between the colors that you see and the organisms that are present. And like any ecology, like a rainforest, there are different organisms like different parts of the structure. And so one of the questions is using these patterns and the information we can get about the organisms to try to understand how you actually get these structures to grow. And we've been working on this for, I guess 5 years ago was the first time we got the funding to really start at this, and we're working our way towards understanding things. We're at the point where everything's very complicated, and we have lots of data, and we don't know the correlations yet. We do know that we're getting, enough new data to publish, and hopefully to get more funding. We've been funded twice now, and just a lot of really interesting ideas and beautiful images. So. When we go, we typically spend a month or so. The amount of time can actually spend, a diver spends underwater is about half an hour, maybe 40 minutes before they get cold. Each diver can dive once a day, so it's like maybe 2, sometimes 3 dives a day, so you get very little time in this physical world. But we do get samples. And so these are from a different lake, and one of the ways the divers collect samples is they take a clear pipe, push it down over some of the structures, cap the bottom, and then we can bring them up and photograph them. And you get all these little bubbles as the pressure releases. And in one of the lakes, you actually get minerals forming in them, so they basically have a skeleton that's growing. They're becoming fossilized as they form. And so we can dissect them and look at the fossil, sort of the interior part of it, which captures some of the layers as they grew. It gives a history of their growth. One of the great things, though, is we can use a mouse scanner in the vet school and measure the density differences. So it's a CAT scanner, like people look at bones. Our cores are about the diameter of the little test subjects that they do the mice in, and we can make these scans that tell you what the density is. And so this has some of the mineral, calcite in here, and then some sand, and then the microbial parts of it are low density. So this gives you a good sense of the mineral components of it. And that's where the virtual world comes in. So what we can do is, like with a medical scan, you now have virtual data that represents the density of the sample, and you can color that, and you can make parts of it transparent and explore it. So here is a sample that's about that tall, and the white parts are the mineral parts for calcite. And so we've mapped the color, so low density is at this end, high density here. So low density would be the ice. The blues and pinks are the microbial biomass, and then you have the mineral grains. The vertical axis here is how transparent or opaque the data are. So we've made the water and ice transparent. The matte parts sort of fog-like, and then the mineral parts more opaque. Then we can do all sorts of things you can't do with a real sample. Like, for example, this is a slice through here, and you can see the sequence of layers. And those layers are reflecting the time of growth of the structure. So it starts out small, and you add material to it, you precipitate more minerals, and you get these amazing shapes that give the history of growth. And through a lot of work, my student Tyler has connected this to the change from these circular patterns to the more blobby patterns is actually related to a change in the bacteria that were growing there. And so we're starting to piece together a little bit of that history. So to publish things and to give you a talk, see things in 2 dimensions, most of the work we actually look at in 3 dimensions. And so we have the cave, part of it, is a virtual reality environment. This is me. My image is captured by 2 Microsoft Kinects looking in each way. And this is Oliver, the main computer scientist, doing the same thing. And so I'll show you a little bit about the cave in a minute. I'm in the holodeck for scientists. Oliver's in front of a 3D TV. And Barack, a third person, is looking at us on a computer screen. And so we're physically in 3 separate places. And this is a virtual image of the sample that's stored in the computer. And the software merges us together in a way that we can interact. You can see that I'm very small relative to Oliver. That's because I'm in an environment I made my sample that's really this tall, about my size. Oliver is sitting in front of a largish 3D TV, but he's made the sample relatively small, so he looks big relative to the sample compared to me. So I'm going to show you a little bit more of this video in a minute with some of the sound, but I thought I'd introduce you a little bit more to the technology. So we have the cave. And so this is the room. It's 8-foot by 10-foot screens and a floor. And the screens are back projected with stereo images. And so it flashes a right eye image and a left eye image alternating on the screen. And then we're wearing the funky glasses, and those have an LCD crystal. And when the left eye image is on the screen, the right eye LCD crystal is opaque, and vice versa. So you really see things in true 3D, even more than in like the 3D movies. There's very good separation between the eyes. And then this guy in the back, with a wire coming out of his glasses and the controller, he's tracked by the computer. And so the computer calculates exactly perfect 3D vision for him. So when he turns his head, it's just like you're in a physical world, and the object responds to you. So we use visual cues all the time. Like I shift back and forth, and I get a lot of visual cues about where people are standing, in addition to the stereo vision from my eyes. That person wearing the track glasses will see a sphere, and it'll look exactly like a sphere. The other people will see something similar, but they're sort of looking through the eyes of the person who's being tracked. And so the sphere might look a little oblong or a little misshapen, but our eyes are very good at sort of accounting for that. And so basically what we do is we take our data and we put it in the cave, and then we can use all the visual processing of our eyes and sort of all the evolution that's gone into our vision to interpret the data in ways that you can't do mathematically. And you're all here, you understand the importance of both being able to see things to understand them and also interact with them.
Virtual reality researchers often talk about presence, which they define as a kind of illusion that you're somewhere else when you're in a cave. But what we're interested in is research presence, which is the degree to which the scientist feels like their data is available to them to manipulate and play with, tweak, and do things with. It's an immersion they have with their own data. So there's never an illusion, but rather their data is available to them in new ways.
And so this is one of our colleagues, Joe, who's really helped us articulate this value of being able to do something you can't do in the physical world. And that's what's going on here.
I'm going to draw in yellow here. And some of these large ones are connected by some of the smaller ones that you showed bending over. We don't know what in the microbial map makes it grow like that yet, or what actually controls where you get the minerals.
So in this particular case, we're in different places, but we're exploring a virtual representation of the sample together, and we can do things you can't do even when you're physically in the same space. So you can have multiple people in the cave, but only one person gets their eyes tracked, and so you have to look at what that person is looking at and doing. Here, where we've moved entirely into the virtual world, I control my vision. So Barack is the one filming this. He's just looking at a screen. He sees me go up and sideways because I've taken the sample and turned it so I'm looking at the top. So for me, I've taken the sample and turned it. For Barack, he sees me as moving relative to the sample because he can control his own view. And so the idea of using a virtual world for science is to do things that you cannot do otherwise. I mean, it's fun to be in there, but it's not fun enough to spend hours in there. It is, I do spend hours in there when I'm engaged in trying to understand a scientific problem. And you know, there's some sort of physical effects like getting dizzy and things like that that affect people, some people more than others. But when you're really engaged in that science, when you have that scientific presence, you know you're not in a real environment. You don't want to be in a real environment. You want to do things that you can't do in the real world. So this, of course, goes well beyond science and inspires a lot of creativity in scientists, in artists, in social scientists, in kids, in my neighbors, you know, and so...
We're always amazed at how much play is a key aspect of scientific work.
Right, so we're trying to sell it often as science, and this is a science facility, but playing is the way you discover new things. And so we've had a couple of really cool collaborations. So the first one was a performance choreographed by the late Della Davidson, who's a good friend of mine. And we used data that was collected for natural disasters by one of our alums in the United States Geological Survey. And we projected it in a 3D screen, movie theater style, in the back during part of this dance theater performance. And then the data extended across the stage and boxes in different ways. And this is laser scan data, and so it has this really nice pointillist aesthetic. And basically it shoots a laser and times the length of time it takes for the laser pulse to come back, and it gives you distance. So it's a very, very precise landscape. And in this particular case, this is a house, and you can looking up into the foundation with the ground had fallen away from it. And so this was a really large effort with Keck Caves for this collaboration, and we won a visual design award for that really meant a huge amount to us as a really important collaboration, where it genuinely used data that we had taken for science in a way that helped express this idea of collapse, both from the natural systems and social systems, and how we integrate with that. You know, in some sense, getting back to Deepwater Horizon, and how do you deal with the things that go wrong. And then I have a collaboration with Meredith, which has grown over the last couple of years. Joe, the anthropologist who spoke a couple of times, arranged some funding to bring people to the cave. I'm not sure how we ever spent the money because people just came. But we had this great group with artists, and Meredith came away with a storyboard for a vortex of dreams and interconnected ideas that one would see in the cave. And you know, a lot of this, the ideas connected with me, but this is actually something that I could envision with one of the programs we actually had. So I responded with a network of my garden, which is very far aesthetically from Meredith's attempt to express what she visualizes aesthetically. But you start with what you have when you're dealing with software.
So what one intends to do with a model colors the nature of the structure captured by it.
Okay, so this is Jim, one of our collaborators, who's I think online for the Berkeley laser next month. But basically, he works a lot with chaos and networks, and I used one of the programs that he and his students developed to get that first bit of the dream vortex together. It's transforming aesthetically in nice ways, but we took, Meredith made these beautiful drawings based on dreams that she first took out from books and then took from us, and I've made a particularly strong effort to give her dreams. But the idea is to combine the Meredith's sort of artistic interpretation with these hand-drawn images into something that's this virtual reality where you can do things you can't really do. And then this is me commanding the cave with my hands, which is one of my daydreams. And eventually the aesthetics will hopefully look much closer to an actual vortex of ideas. And Jordan Van Allsburg has been working with her on the programming to get that. But what we did is we started with something we had. This program has limitations that were structured by what it was intended to do, and by incorporating the new intent and the new purpose with the artistic expression, we can change and adjust that. And we find that when we do that, the different view that comes from an artistic perception helps us think about the science data differently, and we get new insights from it. We have shown it at Maker Faire, both in 2012, 2013. This is on a 3D TV, and it's really, really interesting, again, to have that interactivity, to see how people respond to both the science data and the collaborations. And so this is my last slide. I showed you a couple examples of what we have in the cave. I also work with the Curiosity rover on Mars, and this is one of my favorite projects. We got this CAD model of the rover. We put it in front of images that the rover took in the cave, and I'm standing with it. So this is a model of the rover with images that are really from Mars, from the real rover, with me standing in front of it. And it sort of takes all that sense of sort of real data, engineering models, my presence, and puts it in this whole other world in our solar system. And we actually use this, not exactly the setup of the program, but we use that to try to understand the data that are coming from the rover and to make decisions about what we actually want the rover to do. So thank you.
Before you take questions, lots of references there. So we do have a video, I think, of Meredith explaining the dream vortex in the rock. So you have her version of the story, right? I think you have the video somewhere.
Yeah, Meredith talked at the Davis Laser, and we also talked at Berkeley together.
Okay,
and
well,
that's
hopefully
online.
Just Google it.
Yeah.
Second, I forgot to say about the Jurassic. So you are going to be a resident?
I am, yeah.
Jurassic, Meredith, and Kurt Frank. So
Oh.
Jurassic is, for those who don't know,
Yeah.
it's a art space, but it's outdoors. Huge area. On the hills, was it Santa Cruz? No, it's
It's
Woodside.
Santa Cruz Mountains.
It's still technically Woodside, right?
Okay.
Of the skyline. And you can visit in the summer. There's days when you can go and visit. You can physically hike outdoors and see all the big sculptures. And this year, there's this special program in July. This ladies and gentlemen, 12 total.
Yeah. And Jim Crutchfield, who's one of the physicists we work with, is going as well.
Oh.
Yeah.
Yeah, forgot you. So they will get together, 6 scientists, 6 artists that collide. And then at some point, the lasers will present the results of that. Questions?
Is any of the things you're doing in Antarctica going to be used on some of the probes in the water moons?
No, in the sense that we send people. And we are very, very, very far from sending people to Mars, let alone a water moon. And we're studying biology that has definitely evolved over billions of years on Earth. Some of the concepts behind it and how you actually interpret what you might see on Mars may be relevant if there's life there. So we're looking at a world that's dominated by life. All of those pinnacles are composed of like 99% life, or the organics made by life. If life is sparse, you tend to see mineral grains. So if there's abundant life there, then what we're doing is extremely relevant. If it's not, it's not. You'd actually want to look at a place, a model on Earth where life maybe is present but very sparse to try to understand those worlds. But the work is funded by NASA to get at some of these questions about life.
I'm familiar with cave technology and visualization, telepresence integration. But I'm curious about your personal experience about the kind of leverage that's provided for you, and perhaps an example of a discovery through play or otherwise,
Right.
that you feel that technology really enabled that was not really feasible any other way.
Right. So I didn't show you any of the pictures of the fossil structures we looked at. So in 1990, my first year of graduate school, I saw these amazing fossils of microbial communities in South Africa. And I wrote a couple of papers about them, but they have a very complicated morphology. It's actually a lot like all those little pinnacles that you see. But when you're looking at a rock, you're looking at a two-dimensional surface, right? And so it's really cut through that. And so I spent a lot of time trying to figure out how those peaks were connected. And and what we do with those, we don't get any data from CAT scanning. It's great. I have lots of undergrads working for me, and they grind off the rock, polish it, and scan it with a flatbed scanner every, 100 microns, so just a teeny amount. And then I had used sort of 2D imaging to try to make parts of it transparent and see it, but I had to have too much data that it wouldn't respond well. The first time I saw it in this sort of environment, it wasn't the full cave. We had a much smaller visualization system to get funding for this one. Then I saw, oh, it looks like a biofilm. It was just like this immediate transformation of thinking of it as a fossil to thinking of it as a biofilm. So that's, it's sort of a fundamental qualitative shift in the way I looked at it. There's the first graduate student who got a very specific result in the cave did numerical models. And she had set up this three-dimensional numerical model, and she couldn't get the first computation step to converge. The computer just ran for hours and hours and never set it up. And she had looked through the initial conditions again and again and couldn't figure out where it was wrong. And immediately, as soon as she saw it in the cave, she saw that one of the values was way off, and it led to the mathematics blowing up. And yeah, and it's just like, it was less than 5 minutes in the cave, and she'd already spent several days looking for it.
What about time-based extrapolation of that? Just the axis rotations and stuff. Do you make movies to discover things?
Yeah, so the amazing thing is when you actually see it as a real object, you move your head, particularly if you're wearing the track glasses, if you're responding to it like a real object, you see it differently than you can possibly do in the movie. Because you go, what's that? You just move your head and you can see the relationships between things. And so a lot of what we do is conceptually possible without that full immersion. And when that's the case, people often don't use the cave because it's not super convenient. I mean, you use it for a bit because it's really cool, but then the hard work, it's not that convenient. And so you end up discovering what types of things really need that technology. And understanding these complicated 3D structures does. A lot of the Mars work I can do with the same software on a flat screen for most of it, because it's really mapping on a surface and it doesn't need that. More questions?
Well, I had pretty much the same question. So I'll ask another one.
Okay.
How much does it cost to use the cave?
We do not have a recharge facility. The big cost is setting it up. And so it costs me and my collaborators nothing until something breaks, and then we're going to be in trouble. But we'd like to set it up so that you actually pay for it. So we spent on the order of, I think it was $380,000 building it 7 years ago. The projectors technology has changed enough that we could probably replace the projectors for $150,000, $100,000. So it's a lot of money. The thing that really makes it special is the software, which is being written at UC Davis, and that gives you that real-time interactivity. And that's open source, and it'll run on my laptop.
But once you
But
build the
get
thing, to use it, it's just electricity, or is there
Yeah,
some other
and bulbs. So you have to replace the bulbs after about every 1,000 hours, and it's a few $100s. But so then it's basically the staff to keep the computer systems up to date and working.
It's mostly
Yeah.
living.
Is there any international collaboration? Is there any competition that you have, or how does it work globally?
Yeah, so we have a strong tie with various German research groups, in part because Oliver Kreulos is German and has those connections. So the main facility is housed in earth science and geology, and so we aren't actually trying to spread the technology out there, maybe as much as we ought to. But so we use it for our research, and we sort of left it to the computer science side more to deal with how they get the technology and the software use out, and it hasn't gone that far, in large part because none of us are really interested in the marketing and the documentation of the software and the training and all the support that goes with making it available to people who can't just say, Oliver, it's broken, what do you do? So it's really one of these cases where there's a huge amount of potential, and we haven't developed that yet. Yeah.
Just a comment about that. This technological approach is pretty common in the industry now.
Yeah.
And in research work. And there's a number of organizations that are kind of focused on continuing to inform professionals about where it's all going. One is called SINE, S-I-N-E, RID.
Mm-hmm.
And the University of San Diego is a very strong center for a number of reasons.
Yeah, we've interacted with them actually. Yeah, and one of the things that makes this different, and the people, I mean, this is really housed in geology, and geologists use it, and so it has a very different focus than most of the computer science run type things. And when they first came to visit the cave, Oliver insisted that me and another geologist demo it. And at that time, it was all terminal commands to get it going. We didn't have things you click. And I didn't know those. I mean, I had just learned the bare minimum, and they actually had a hard time believing that I, as a scientist, was running things independently. But that's sort of the way it's set up. And so there's sort of this disconnect between what we're doing with it and what a lot of, I know the San Diego group in particular sees the computer science side of things should be. It's a very interesting cultural disconnect, I think.
I think each organization has a slightly different emphasis in the sector, but companies like Caterpillar have their own caves.
Yeah. No, I know, and oil companies definitely do. I'm a geologist, I know oil companies, yeah. And when we brought people from oil companies in, we use it very differently than they do. And the geologists say, we just use it to convince our managers that we're right, and they don't actually do their work on it. That was a while ago. I haven't talked to them in the last few years, and it changes.
Okay, thank you very much.